Welcome everybody. So today we're going to talk about uniform circular motion, which is a special case of the angular motion that we have been talking about. Uniform circular motion describes an object which is going around a circular path at constant speed. So I've drawn a quick motion diagram for such an object, which I've labeled both velocity and acceleration vectors for. Again, I'm moving at constant speed, so all of the velocity vectors have the same magnitude, even though they're always pointing tangent to the curve in different directions. And then I know I'm moving around a path, and again with constant speed, so I should have some centripetal acceleration, which I've drawn in green here, but that there will be no tangential acceleration to speed up or slow down the object. I also know I'm moving around a circle, so I've labeled the radius of that circle here. And I'm going to write down a few pieces of knowledge that I can draw from this particular situation, because there are a lot of situations out there in the real world that can be well described by uniform circular motion. So one of them we already know is we have some constant speed that we could write as v. We also know that we have a constant radius r. And we know from what we've talked about with angular motion that there's a relationship between the translational velocity, or the translational speed v, and the angular speed omega, and that those two things are related by an equation like this one. Which means that if I've got a constant v and a constant r for uniform circular motion, I also have a constant angular speed omega. Furthermore, this centripetal acceleration is going to follow what we already know about centripetal acceleration, which is that it looks like v squared divided by r. Again, both of these things are constant, which means the magnitude of the acceleration vector doesn't change, even though the direction changes, so that it's always perpendicular to the surface of the circle. Again, we know this relationship between v and omega, so if we want, we can rewrite this expression in terms of omega by solving this for v, plugging it in here, canceling out one factor of r, and writing this as r times omega squared. This is just a way of rewriting information that we already know here, but maybe you're given omega instead of v, and this becomes a more versatile equation to make use of when talking about circular motion.